Today we're going to tackle a question that sounds really simple, but the answer, well, it's almost certainly not what you think. And the question is, why do we even have seasons? I mean, it's a rhythm that runs all of our lives, right? You've got the blistering heat of summer, which eventually gives way to the biting cold of winter. But what's actually physically going on to cause that huge shift? Now, the answer that just feels right, the one that makes the most sense, is that we must get closer to the sun in the summer. Stand closer to a campfire, you get warmer. Simple logic, right? And yet, that perfectly logical idea is completely wrong. In fact, NASA calls this the single most common misconception people have about our planet. So, okay, if it's not the distance, what in the world is it? Okay, get ready for this, because this is the part that blows your mind. When it's summer in the northern hemisphere, let's say peak July heat, the Earth is actually at its farthest point from the sun. No, really, we're millions of miles farther away when we're sweating through a heat wave. That just demolishes the whole distance idea, doesn't it? So that brings us to the real reason. The hero of this whole story isn't how close we are to the sun. Nope, it's all about our planet's permanent tilt. See, our planet doesn't spin perfectly upright while it's going around the sun. Imagine a spinning top. Earth is more like one that's leaning over a lot. It's permanently tilted at an angle of 23.5 degrees. And that little lean, it changes absolutely everything. The fancy term for this is axial tilt. And here's the really important part. As we orbit the sun, that tilt always points to the same spot out in space. It's kind of frozen in that position. So what that means is, for half of the year, the top half of the Earth, the northern hemisphere, is leaning towards the sun, and for the other half, it's leaning away. So what does that leaning actually do? Well, it creates this huge difference in the kind of sunlight we get. And the best way to understand this is with a super simple analogy I like to call the flashlight effect. So remember, it's not about being closer or farther away. It is all about the angle of that sunlight. That tilt means the sun's rays hit our planet at different angles, and that completely changes how much heat and energy actually get to the ground. Think about it like this. When your half of the planet is tilted toward the sun, the light hits you straight on. It's like shining a flashlight directly at a wall. You get a bright, focused, intense circle of light. That's summer. But when you're tilted away, that same sunlight hits the ground at a low angle. It's like shining that same flashlight at the wall from the side. The beam gets all stretched out, bigger, but way dimmer and weaker. That's winter. And we're not talking about a tiny little difference here. A sunbeam that hits the Earth at just a 30-degree angle delivers only half the energy compared to a beam hitting straight down. 50% less heat just because of the angle. That's huge. So this little trick of geometry has this massive consequence for the whole planet. Whenever one half of the world is basking in summer, the other half is, well, it's stuck in winter. It's like a perfect mirror image across the globe. So picture it. In June, the northern hemisphere is leaning into the sun, soaking up those direct rays. Hello, summer. But at the exact same time, the southern hemisphere is leaning away, getting those weak, spread-out winter rays. Fast forward to December, and poof, the whole thing flips. Now it's the South's turn for summer. And that is why someone in New York dreams of a white Christmas with snow and hot chocolate, while someone in Australia is planning a Christmas barbecue on the beach. Same day, same planet, same sun, but completely opposite seasons, all thanks to that 23.5-degree tilt. But hey, this whole axial tilt thing, it's not just an Earth show. It's a universal law of physics. And when you look at other planets, you see how this rule can create seasons that are, well, let's just say they're pretty extreme. Let's start with Mars. Its tilt is actually pretty similar to ours, but its atmosphere is super thin. So what's a summer day like? Well, recently, the temperature in one crater hit a peak of -18 degrees Fahrenheit. Yep, that's their idea of a summer heat wave. Okay, how about Saturn? Again, a similar tilt, but it takes 29 years to go around the sun. That means a single season, just one, lasts for more than 7 years. Can you even imagine a summer that goes on for 7 years straight? But the real wild one is Uranus. This planet is basically spinning on its side. It's so tilted over that each pole gets 42 straight years of nonstop sunlight, and then it's plunged into 42 straight years of complete darkness. Talk about extreme seasons. All right, let's bring this all back to Earth for one last really fascinating idea. That tilt we've been talking about, the thing that gives us everything from summer vacation to winter storms, it's not set in stone. Over really, really long periods of time, Earth's axis actually wobbles, kind of like that spinning top again as it starts to slow down. It slowly rocks back and forth between about 22 degrees and 24.5 degrees. It might sound like a tiny change, but for our planet's climate, the implications are absolutely massive. This whole wobble cycle takes about 41,000 years to complete. If you go back in time, say 10,000 years, the tilt was maxed out, which meant more extreme seasons, hotter summers, colder winters. Right now, today, we're kind of in the middle of the range. And looking forward, in about 10,000 years, the tilt will be at its minimum. That probably means the seasons will be a lot milder than what we're used to. So let's end on this thought. We've just seen how our entire world, our climate, our culture, pretty much our whole way of life is shaped by this one specific number, our 23.4-degree tilt. So it makes you wonder, doesn't it? What's the world going to look like for people thousands of years from now when that fundamental angle is different?